Good evening, everyone. Uh, is my voice clearly audible, Karthik? Yeah. Okay. Okay. Thanks for confirming. Okay. So let's get started. Uh, Actually, this week my writing pad is not available with me, so I will mostly discuss the questions based on concepts we have seen in previous week and in the content of the ongoing week. And I will also refer to some of the notes of my previous discussion hour. And in case I really need to draw something, I will try to draw it using my trackpad. So just bear with me for this discussion hour. So yeah, let's get started. Okay, so let's in the last discussion hour we discussed, if you have seen the videos on the YouTube channel, we saw about the Jacobian and their relation between the end effector velocities and the joint rates, as well as the relation between joint torques and the end effector forces in the static case. So we saw what's the importance of the Jacobian matrix of a manipulator in relating quantities in the task space to the quantities in the joint space. So we'll see a few questions around these concepts and some other related concepts. So as we go through the questions, I will explain the related concepts, and if there is any doubt, please feel free to point them out. Okay, so let me share my screen. Hmm. Okay, so the first question says the Jacobian matrix relates what quantities? And as I just summarized, and we have seen in, I think, now 2 weeks lectures that the Jacobian relates the end effector velocity and joint velocities. So the end effector velocity is in the task space or the Cartesian space, and the joint velocities is in the joint space, or also called the configuration space. So x dot is equal to j theta dot is the usual relation which we have. So yeah, I will refer to some of the written notes which I have. So this is the relation x dot is equal to j theta dot. Okay, yeah, yeah, go on, Karthik. So in what context did you get confused between them? Can you just let me know more about that? Aha, okay, okay. Yeah, I remember that. I remember that. Yeah, I got it, got it. So let me explain that. Yeah, yeah, yeah. Yeah, I recall that. I recall that. So what I was trying to put across there was that if we want to specify a trajectory for the end effector, right? So the trajectory is a sequence of points through which we want the end effector to move, right? Okay, so in the physical space, like in the so if let's say we have a 2R manipulator, right? So the space in which it can move is the 2D plane. And the 2D plane is represented using the X and Y coordinates, right? So the trajectory can be specified in either of in the task space or in the Cartesian, or in the joint space, right? So trajectory is I would say, a quantity which can be expressed either in task space or in joint space. In task space, we will express it as a series of x and y coordinates, right? So let's say the starting point is 1 comma 2, the ending point is 5 comma 10, and let's say I fill the x coordinate between them using linear interpolation, and similarly y coordinate between 2 and 10 using linear interpolation. So there will be a series of these xy coordinates, right? 1 comma 2, 1.1 comma 2.1, 1.2 comma 2.2, and so on, right? Just give an example. So if I express the trajectory like this, then I would say that a trajectory is expressed in the task space, right? Now the same trajectory, if I have it specified in terms of x comma y, then I can also convert it into trajectories of joint angles, right? That in order to follow that trajectory, right? What is the trajectory of my joint angles, right? So here's the difference between the two descriptions. So why I gave that example, the motivation behind that is that our physical world in which we will specify the task generally would be in the task space. That's why it's called the task space, because I would like my manipulator to move from point A to point B, and that this and the coordinate I would know the coordinates of those points, right? Let's again let it be 2D or 3D space. I would know the coordinates. So it will be not very intuitive to specify the trajectory in terms of joint angles, because I would not say that okay, I want to move from joint angle 30 comma 60 to 40 comma 50. Like it would be not very intuitive to me that what will happen if I do that, right? So what is more intuitive or more makes sense to me as a user of that, let's say arm, is that I want to move it from 1 comma 2 to 3 comma 5 in the 2D plane, right? That I can visualize very clearly, right? Yeah, and once we define that trajectory in the task space, I can always, using inverse kinematics as we have seen, we can always convert it into the trajectory in terms of joint angles. Oh, so there's a question in the chat which says, when you define trajectory in joint space, do we have intention to define speed also at which we might plan to follow trajectory? Which may be, yeah, of course, like trajectory also includes the information about velocity and acceleration. So right now I am not talking about them, but of course, if in a practical scenario, if I would like to specify a trajectory, I would also specify that what would be the velocity of the arm. So let's say uh, there could be again different ways to specify that also. Like let's say if I could give it again a variation of velocity also, or it could be that I want to move from one sample point to another sample point of the trajectory, and the and the time moving from those 2 points is the same. So let's say there are n set of coordinates, let's say x1 x2 x2 like xn. So there are a set of n coordinates, and from each xi to xi plus 1 I move in delta t time, right? So using that you can get the velocity also. This could be a way to specify the velocity, or else I could give a separate trajectory, separate polynomial for the trajectory also, that the trajectory will vary like this. So yeah, I have in practical application, I have intention to specify the velocity also, because I am also concerned how fast I move from point A to point B, because I should move that fast only which my actual motors allow, right? In some sense. So I cannot move arbitrarily fast between point A to point B. So I might imagine to color the trajectory as well according to speed. Yeah, I think if you're talking about visualizing the trajectories, you can always do that. Right. Right, Trevor. And of course, like you can pitch it, like you can directly ask the question in chat. I might in by unmuting yourself. I might miss few questions in the chat. So I hope that's clear. So trajectory is something that we specify usually in terms in task space, because that is more intuitive for us, and for our computations of basically when we will talk about following that trajectory and how to control the position of the end effector, and when the control comes in the later part of the uh, course, then we will see why we need to convert it to joint angles, and then basically we will need to follow those joint angle trajectories using some PD control. So that's the other part of the story. And finally, we will see the whole picture, that we'll have to apply some joint torques throughout the motion, and those joint torques will be calculated using what is our current joint angle and joint rate, and what is our desired joint angle and joint rate. And basically, in a simple controller would be to apply a PD law, a proportional and a derivative controller, and try to follow that desired joint angle trajectory and desired joint rate or joint velocity trajectory. So that's the bigger picture of the whole following a trajectory and using a manipulator. So in entirety of that process, Jacobian will play a part. So that comes at the very first step, which we are seeing right now. Karthik, does that answer your question? Hmm. Yeah, yeah. Task space is the 2D plane. If it's a two-hour manipulator, it's a 2D plane. If it's a 3-hour manipulator or a non-plan a plan manipulator which can move in the 3D space, then the task space is the entire 3D space, the Euclidean space, X, Y, Z. Yeah. So the task space is the XYZ space, and the joint space or the configuration space is the space of theta 1, theta 2, theta 3. Right. So those are two spaces. And we switch back and forth between these two spaces using the Jacobian. Okay. So the next question is if the determinant of the Jacobian is equal to 0, then what happens? So again, using the same relation, we have that joint rate is equal to inverse of the Jacobian times the end effector velocity. So once we have the inverse of the Jacobian, the inverse of a matrix does not exist, when the determinant becomes zero. So if it's a square matrix, and that would be the case if the manipulator is non-redundant, so then the Jacobian will be a square matrix, and the determinant of a square matrix will be adjoint of J by determinant of J, right? And when determinant of J goes to zero, so this quantity will also go to infinity. So joint velocity will tend towards infinity as we reach towards a position where determinant of the end effector is zero. And that is the location where we say the manipulator is at a singular configuration. So as we go close to a singularity or a singular configuration for a manipulator, the joint velocities increase very rapidly. And that's the reason why we would like to avoid such positions while planning our trajectories in practical applications. And the next question pertains to the same concept about singularities. So singularities are points in the workspace where determinant of the Jacobian becomes zero. So again, that's the point which I explained right now. And so for any manipulator or any multi-body system which we will have, so we can find out the Jacobian matrix, we can find out the expression of each of the terms, and then calculate the determinant and find out what is the configuration of the manipulator at which we will attain the singularity. So that's the one way of finding out singular configurations. Uh, you would remember in our, I think, week 3 discussion hour, I had shown how to find out for 2-hour manipulator, and this will come again in as a question in, I think, yeah, this is the question. So, what for a 2-hour manipulator, what is the configuration in at which uh, the manipulator is singular, right? And the way to approach these type of question is to find out the Jacobian matrix. So as you see here for question 4, for a 2-hour manipulator, now you would be quite comfortable in writing the Jacobian matrix. So how do we write the Jacobian matrix? We write the position of the end effector x comma y in terms of L1, L2, theta 1, theta 2. Then we differentiate, right, each term with respect to theta 1 and theta 2. Then we get the Jacobian matrix, right? Does anyone have any doubt in writing the Jacobian matrix for 2-hour manipulator? Okay. So once you have the Jacobian, then your task is half done. You just have to find out the determinant, and determinant of a 2 cross 2 matrix is Quite simple. It's uh, cross. You just multiply the cross terms, right, and subtract them. So it comes out to be L1 times L2 times sine of theta 2, right? So the determinant clearly depends only on value of theta, not on theta 1. So it goes to 0 when sine of theta 2 goes to 0. And sine of theta 2 goes to 0 for theta 2 is equal to 0 or 180 degree, right? So those are the configurations in which the 2R manipulator is said to be singular, right? So wherever the physically it will, as you will remember, it corresponds to the arm locked out position and fully extended and arm fully retracted, right? So it can't reach beyond that, it can't reach any closer to that. So that's the configuration. Can you hear me properly now? Okay, okay. Yeah, thanks for letting me know. Okay, so those are the two positions. So I was saying, if I will just repeat quickly. So the positions corresponding to theta 2 is equal to 0 is the arm fully extended position, and corresponding to theta 2 is equal to 180, it's the position in which the arm is fully retracted. So, as you would remember, we drew the workspace of the 2R manipulator, and if the second link is smaller than the first link, then it turns out to be a annulus or a ring, right? And at the boundary of that workspace, we have the singularities. So for 2R manipulator, the singularities which we have are all boundary singularities. I think I have this. Let me just pull the notes of previous lecture just to review it. Yeah. So that's what we did, right? L1, L2 sine theta 2. We found out theta 2 is 0 or 180. And we saw that this is the annulus or the ring, which is the workspace of the 2R manipulator. And at the boundary, the inner boundary and the outer boundary, we have the singular position of the manipulator, right? And the related question to this only is was the minimum energy configuration for a 2R manipulator, right? So again, the minimum energy configuration would be when determinant of J will be maximum, right? So adjoint of J by determinant of J and determinant of J will be maximum. So that's the position when the joint rate or the joint velocity will be minimum. And we know that the kinetic energy of the manipulator will depend on the joint rate, right? The square of the joint rate. So if we minimize the joint rate, then we'll also minimize the energy, right? So what we will have to find out is at what values of theta 2 determinant of j is maximized. So that will be possible when sine theta 2 is plus minus 1, right? So that is when theta 2 is 90 or 270. So that's the position when the angle between the first link and the second link is 90 degrees. So that's elbow bent position. And that's the position when the manipulator uses the least amount of energy. All right. So now the next question is about the static uh, force and moment analysis for a manipulator. And this is what we had discussed at length in very detailed manner in the previous discussion hour. And I will use notes from the previous discussion hour to again explain this concept to some of you if you have not joined in the previous discussion hour. So let me set the picture here. So what we have is we have a 2R manipulator and we are applying a force, uh, again a 2D force that's in the plane of the manipulator at the end effector. So that is F3 given as Fx, Fy, and 0. So the Z component of the force is 0. And due to this force, the manipulator will experience, or the joints and the links, they will experience some torques and forces, right? So we have the concept of force and moment propagation, right? That if I apply a force at the end effector, then how does it the affect all the other links in the chain, right? And how does it affect the joint torques at all the joints in the mechanism, right? So let's use this note in order to go through that, right? So we have to do two things. We have to do force balance and we have to do moment balance, right? So for force balance, since this is a static case, what we have to do is that we have to just equate the forces acting on the link. So the total force, the sum of all the forces acting on the link should be zero, right? So if the final link, if we are applying a force F on the final link, then there will be a reaction force that will be applied on the joint, right, at the joint with the first link, right? So since we are considering static case, there are there are no accelerations, right? And we can just say that Fi is equal to Fi plus 1, right? And again, yeah, yeah. So since I have written in terms of vector, so when you will write it in with sign in terms of like sign and the component, so there you will take care of the direction. So here, like the vectors, you can basically say that Fi. So here it will be Fi minus Fi plus 1 is equal to 0. And why minus Fi plus 1? Because it's the reaction of the force F on Fi plus 1, right? So indirectly what I'm saying is that, let's say if I'm applying plus F on the I plus 1 link, okay, okay, is it clear now, better now? Okay, so what I'm saying is that, let's say we have the so let's use this picture as a reference. So if F3 is acting on link 2, right? So the reaction force that will be acting here at this joint would have to be in opposite direction of F3, right? In order to balance it. Am I right? Because so again, so because this link, this L2 link is in static equilibrium, and no other forces are acting on it. So the only force that will act on this at this joint would have to be equal and opposite to this F3, right? Okay. So F3 will be pointed in the other direction, opposite of this this F reaction will be just equal and opposite of F3, right? So basically that's the whole concept, and you will take care of the signs and all when you will be actually writing the uh, vectors and their components. So I mean, just keep that concept in mind and don't get confused whether if there should be a minus sign or plus sign. So that depends on what notation is being used. So here, since Fi plus 1 is the you know uh, reaction of the force being applied on the ith link. So I think that's why the minus sign is not there. The that The bottom line is that on any given link, sum of all the forces should be zero. And when you will be writing this, just take care of the directions in which all the forces are there, right? And we saw in the example also. So again, I will go through the example. So maybe it will be clear. And again, we will clear it again at that time too. But the bottom line is that in static equilibrium case, sum of all the forces is zero. Sigma F is equal to zero, right? And sigma F is the sum of all the forces acting on the given body. So you will analyze each body. So in this manipulator, each link is a rigid body, right? And while doing force analysis, statics or dynamics, we pick each rigid body individually and we write the force balance and the moment balance for them. So it's a very, really, very problematic way of doing things. Sorry for that. So you pick each rigid body and write force balance and moment balance for it. Since we are doing static case, there are no accelerations or angular accelerations. So sum of all the forces, sigma F, acting on the body is equal to zero. And similarly, sum of all the torques or moments acting on the body will be equal to zero. Right? So that's how these two relations we are getting. Okay. In the second relation, also the moment balance, but we are just doing that. The joint torque which will be experienced at the ith joint will be equal to reaction torque plus the torque due to the force applied. If there would be an acceleration, angular acceleration, then we would have had additional terms. But since here there is no acceleration, so everything should cancel out, right? So whatever is the source of the force, it should be cancelled out by a equivalent and opposite reaction of that force or moment. Okay, so that's the only thing which you have to keep in mind, and just stick to this concept. That will help you avoid getting confused in different scenarios. And you can always derive or write these relations on your own whenever you are solving these questions. All right. So again, this example is what we discussed in last class, and I will just go through it once again. So yeah, so the force on the end effector F3 is Fx, Fy, and 0. So the moment acting on joint 2, which is N2 here, and the notation again I will recapitulate is the subscript on the right hand side is denotes the joint I am talking about. So N subscript 2 is the joint torque at joint 2. And the superscript on the left hand side is the frame in which I am describing or writing that vector. Okay. So again, if you refer to the uh, point where I'm discussing this or the initial part of discussion hour 4, you will find that I have described in detail, what is the this type of a notation mean and how does uh, writing a vector in certain frame and differs from what that vector actually physically denotes. So I have elaborated how to not get confused in that. So N2 joint torque at the second joint expressed in the second frame. The second frame is attached to the second joint, and the z direction of that frame points outwards of the plane. Okay, so that is L2x2 cross the force at the end effector. So basically, torque is equal to R cross F. So R, that is the position vector from the origin or the axis to the point of application of the force. So from the origin of frame 2, which is here, to the point of application of the force, which is at the end of the link, So that position vector is L2 and the direction is x2 cap. So L2 x2 cross with the force, right? And we did the cross product and we got L2 Fy Z2 cap, right? So Z2 cap is the axis of the joint 2. And if the question, the first part of the question number 6 only asks what's the torque acting at joint 2. So that we got very easily. And the correct answer is 0, 0 L2 Fy. So any doubt still here? Anyone? Okay. Now, okay. So now the second part, that is the joint torque at the first joint. It's not in the previous year questions, but let me just go through that also because that has some more details and has more calculation than calculating torque at joint 2. Okay. So L2 Fy Z2, once we got the torque at joint 2, then for link 1, right? So this is joint 1 at the base. And first, let's do the force balance. So we have to find what is the, we have to write what is the force acting on the first link expressed in the frame, the first frame. So that is same as force acting on the second link because of the static force balance. And this rotation matrix is being pre-multiplied to this vector in order to convert it from frame 2 to frame 1. So again, the vector remains the physically we are not rotating the vector. Rather, we are just describing the same vector in another frame. So on the right hand side, the force vector is in the second frame. On the left hand side, the force vector is in the first frame. Okay, so the rotation matrix is given like this because it's a rotation around the z axis. So the third row, third column component is 1, and the rotation is by theta 2 angle. So the usual rotation matrix cos theta 2 minus sin theta 2 cos theta 2 is there, and we multiply to get the expression of force on link 1 expressed in the first frame, right? And now finally, to get the joint torque at joint 1, we add the reaction torque of joint 2. So reaction torque due to the torque at joint 2 and the torque generated due to the force applied F1, the force which is applied at a distance L1 from the axis of joint 1, right? So this expression which I have boxed here. So two sources of generating moment at joint 1. One is the reaction torque due to the torque at joint 2, and the other is moment of the force acting on link 1, right, at a distance L1 from the axis. So again, just writing these quantities very carefully in and note that I have chosen frame 1 for this entire expression. So again, I will reiterate that whenever you write these expressions, initially you can write them in a vector independent notation, but finally in order to solve them, you have to choose, sorry, I will repeat, not a vector independent, but a frame independent notation. But before solving them or before explicitly writing the components of the vector, we have to select a frame. So at the time of writing the components, the selection of frame has to be done. And here I have selected frame 1 to write this expression. So on both left hand side and right hand side, the frames should be consistent. All the quantities should be expressed in the same frame, right? If not, then there will be uh, wrong calculations. So the joint torque at joint 2 in frame 1. So that is same as this L2 Fy Z2 because Z2 cap and Z1 cap are parallel, right? Because since Z2 and Z1 both point out of the plane, so there is no rotation between them. They are parallel. So this vector remains the same, 0, 0, L2 Fy plus L1 x1 cap. So L1 x1 cap is the position vector of the point of application of the force, which is at this joint and from the origin of frame 1. And this is x1 direction, right? So L1 x1 cap cross with the force F1 expressed in the first frame, which we just calculated here, right? So we write putting the same value here, and after that it's regular some mathematical simplification in order to finally get this expression, this n1 expressed in the first frame, and this is 0, 0, and the z component is non-zero, which is expected because it's a 2D manipulator. It should only experience moment in the z direction because that's the direction in which it's allowed to move. The joints have degree of freedom along that direction only. All right, so that's how we can do static force and moment analysis for a 2-hour manipulator. Again, in order to, uh, I would suggest that those who have not seen previous discussion hour videos on this specific example, please watch them. I have discussed them in some detail there. So, so the next question is, uh, manipulation ability is defined as. Any questions? Hmm. In this or the notes? Okay. Mm-hmm, 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 mm-hmm. Yes, yes, yes. Exactly. Right. Mm-hmm, mm-hmm, mm-hmm. Yeah, so the moment will be created by the force which is applied at joint 3, not at the end effector. Yeah, like that's the way we basically that's the way we propagate it so that we do not take into account, few quantities twice. So so that's why, like, you have to be careful. This, if you see the expression here in the terms of i's, so this will be reaction torque part and the force at the I plus 1th joint. So when you will be writing for joint 2, it will be force at the joint 3, not at the end effector. Yeah. So, so, you will start from the end effect, like you will start from the outermost joint, that is joint 3. So, joint 3, there will be no reaction torque, only force moment due to the force at the end effector, right? That will be done. Then you come to joint 2. Joint 2, there will be a reaction torque due to torque at joint 3 and a moment due to force at joint 3. So that is the total torque at joint 2. And then you come to joint 1, then there will be a reaction torque due to torque at joint 2, and there will be a moment due to force at joint 2. So that will be total torque at joint 1. So that's how you start from the outermost joint and then come to the innermost joint. Okay. Okay. So the next question relates to manipulability and just the basic definition of the term. So manipulability is defined as ease of movement in a particular direction. So this is like very, uh, a very generic definition, just the meaning of the term itself. Okay. The next question is the major axis of the velocity ellipsoid is found by. Okay. So I would have loved to draw, the ellipsoids here, but let me just see if I can do with my laptop. Yeah. So this will not be as accurate as the pad. Ah, nice. Okay, so not that accurate, but let me. The two directions. And what we have is we have sigma 1 and we have sigma 2. So you would have studied about Jacobi. Uh, so you would have read about the singular value decomposition in the lectures. So SVD is a very useful, mathematical operation which we do. And what is it does basically. So let me just talk briefly about SVD here and what it makes, what it does physically. So I will go to an image which I had put later in the notes. So is this image clearly visible? Okay. So now what this image is depicting is that there is a matrix M, and M can be a non-square matrix also. So there is no restriction on the shape of M. It can be either square, non-square, and non-square also can be of two types. It can be a flat matrix. A flat matrix is basically in which the number of columns is more than the number of rows, so it looks flatter, and it can be a tall matrix also. A tall matrix is which has more number of rows and lesser number of columns. So they are loosely called as flat matrices and tall matrices. So M can be any matrix, right? So what a matrix, when it is multiplied to a vector, you know, actually, what does that mean in physical sense? So a matrix is a linear operator. Matrix multiplication is a linear operation, right? And it is a combination of two things. It does rotation and it does scaling. These are the only two operations that a matrix multiplication can do. There is no third operation which a matrix multiplication to a vector can do, right? So when I multiply a matrix to a vector, it will either rotate it or scale it or do both. So whenever from now on, if you see a matrix multiplication, you should and multiply it to a vector. Like if you see y is equal to a times x, then what you should visualize is that x is being, you know, x is being rotated by some degree, then scaled by some degree, you know, and that's how y is being created, right? So basically, if you see the picture, so there are four images here. There is a circle on the top left side. So that's a circle, right? And when that circle, so that circle, let's say shows the two vectors, the two unit vectors, the red one and the yellow one. Those are the two unit vectors. Now that circle is being acted upon by matrix M. Okay. And that transformation that is being shown by a arrow over which M is written. So when that circle is acted upon by M, it transforms into a ellipse. And that ellipse, you see that to transform a circle into an ellipse, you have also first stretched it, then also rotated it, right? So it's a combination of scaling and rotation. Now, this is the direct transformation from that circle to the ellipse, the final ellipse. Now, this transformation can also be broken down into individual rotations, scalings, and then a rotation again, right? So that's what SVD or singular value decomposition does. Okay, so M can be written, any matrix M can be written as a multiplication of three matrices U, and typically they are denoted as U times sigma times V transpose. And this V star is basically a more generic expression. It is the for if it is the notation we use for complex matrices, right? So what U and V do? U and V represent rotations. They are orthogonal matrices. And sigma, the matrix in between, is a diagonal matrix, right? And diagonal matrix, which denotes the scaling component. So the first is V star, which is a rotation. It's an orthogonal matrix. Then you scale it, so multiply with sigma. So then the axes get scaled, they get elongated, shortened, whatever, depending on the values of sigma 1 and sigma 2. And then they are rotated once again by application of U. So rotation, scaling, and rotation again. So basically, what SVD does is that it gives us the insight into how much a matrix rotates, and how much it scales. Okay, when it is multiplied to a vector. Any doubts here? Okay, so so and also important things to note about, and I would suggest you read further about SVD. A good starting point would be to just read the Wikipedia page, and then to read some good textbook on linear algebra to know more about this if you want to. So SVD decomposition or singular value decomposition is not unique, right? The matrices U and V can be arbitrary. They will be orthogonal. Depending on the choice of U, V will change and vice versa. But the singular values are the same. So for any matrix M, its singular values are unique. Okay, so sigma 1 and sigma 2 are unique. And in robotics, this SVD of a matrix comes up when we discuss manipulability. Okay, so basically, what we form is the manipulability ellipsoid. So there is a quantity JJ transpose. Okay, so what we do the SVD of JJ transpose, and using the similar values of JJ transpose, we see what's the shape of the velocity ellipsoid. Okay, so the shape of the velocity ellipsoid at any point of the manipulator gives us the idea of how much it can move in the two directions. Okay, so let me again, I should have drawn at this point, but let me pull up the textbook here because it will have figures. Hmm. Hmm. Yes, that is what I wanted to show you. Right. So, so this is the this figure shows manipulative ellipsoids at different points in the workspace of a 2-hour manipulator. Okay. So you see that uh, yeah. So basically, there is a quantity defined as manipulability measure. Okay, and that is determinant of Jacobian times Jacobian transpose. So why did we do JJ transpose? In order to make J, which can be a non-square matrix also in case of redundant manipulators. So if let's say J is M cross N, M rows and columns, then if we multiply it with J transpose, which will be N rows M columns, then JJ transpose is guaranteed to be a square matrix. And for a square matrix only, we can take determinant. So determinant of JJ transpose, and if we do under root, so we define this quantity as manipulative measure. So the higher the value of W, we say that the it has high manipulability in that configuration. Okay, so for a 2-hour manipulator, right, which is not redundant, it is directly equal to manipulability is directly equal to mod of determinant of J theta, right? So J theta is the square matrix for a 2-hour manipulator, and just mod of determinant of J theta. Now, if you remember, the for a 2-hour manipulator, the determinant of J is L1 N2 sine theta 2, right? So mod of L1 N2 sine theta 2, which is basically L1 N2 times mod of sine theta 2. Now, as theta 2 varies, sine theta 2 will change, right? So you can now very well tell that at what configuration the manipulability of a 2-hour manipulator is at highest, right? When sine theta 2 is basically 1, right? And if you would remember, that is the position when theta 2 is 90 degree and 270 degree. And it's the same position, interestingly, it's the same position at which we had found out the energy is minimum, right? So that's the same position in which manipulability is also maximum for 2-hour manipulator case. And when will be W be minimum here? So minimum can be 0, right? Because it's a mod, so the minimum it can go is 0. And it will be 0 when sine theta will be 0, which will be the case when theta 2 is 0 or 180 degree. And again, interestingly, these are the joint angles at which the manipulator is at a singular configuration. So the manipulability is least, right, when the manipulator is in singular configuration. So this again puts weight to the claims which I was making in previous discussion hours, that when the arm is fully extended or fully retracted, it loses 1 degree of freedom, right? So now you see that it is actually related to another quantity called manipulability, and you can relate both these concepts, that manipulability is the ease of moving in any particular direction, and since we are losing the ability to move in one direction at those configurations, theta 2 is equal to 0 and theta 2 is equal to 180 degree, so manipulability should be less there. It makes sense that this definition of manipulability, it makes sense that it comes out to be the least at those positions, right, at the singular positions. Any confusions here in how manipulability measure is calculated and what does it mean? So it's not a very involved concept, but a very useful one in order to, do the workspace analysis of a give any manipulator. Because we always go back to the 2-hour manipulator because it's a very simple example to motivate things in a classroom setting. But while working with higher degree of freedom manipulators, you would have to carefully, and in fact, while designing manipulators, you would have to analyze your workspace very carefully, that where are the positions where your manipulability is highest or the least, and how does it affect your ability to do the task for which you are designing the manipulator. So basically, and in the book also, this chapter is like, is this, you can see the topic of the this discussion, designing well conditioned workspaces, right? That how to design a workspace where the manipulator does not lose its degrees of freedom, right? So these quantities are helpful in this analysis. Okay, so returning back to our questions. So similar values of a non-square matrix A are the square roots of the non-zero eigenvalues of A transpose. So this is a straightforward mathematical result. I showed you that in order to, so you can see this derivation in again a mathematics textbook, that the singular values sigma 1 and sigma 2 or sigma i's of a non-square matrix A is related to the eigenvalues of the square matrix A transpose, right? So lambda I of A transpose is equal to sigma I of A square, right? So let me write it here. Lambda I A A transpose. Okay, so this is the relation between similar values of A and the eigenvalues of the square matrix A transpose, right? So, and finally, the last question in this set of assignment is the SVD of a matrix breaks it up into, again, this is what I motivated just now, that it breaks, SVD breaks the matrix into two orthogonal matrices and one diagonal matrix. So the orthogonal matrices, they correspond to the rotations operation of the matrix or the original matrix, and the diagonal matrix correspond to the scaling operation of the original matrix. All right. So these are the questions on concepts of week 4. Now let's see a few questions on concepts from week 5. Any doubts, queries? There's something in the chat. Can you show force acting on the base joint as well? That we clear. So far it looks like no force. Yeah, well, I showed you the joint torque at joint 1, right? For the 2-1 manipulator case. So that's the base joint here, there. And we saw the joint torque that is there. And yeah, okay, so you're talking about the force. Huh. There will be a force at that joint also, and that will be again same as the equal and opposite of the force acting at joint 2, right? So if you would see here in this example, so force is acting on the this end effector. So if you isolate this rigid body link, right? The link 2, if you isolate it, then there will be a force at the end effector and a reaction force at this joint, right? If you isolate link 1, then there will be a reaction force at this end and a reaction force at this end from the this joint. So that's how we are, and those are the two forces which we are equating, right? So yeah, we are considering forces at each of the linkage points. All right. So I would again suggest that in any analysis, do not picturize the entire manipulator in one go, right? That's not the way to solve the problems. In multi-body dynamics problems, we isolate each rigid body, right? So if there are two links, then draw each of the links individually and draw all the forces and moments on those links individually, which is basically the term free body diagram, right? So free body diagram and drawing that correctly is the most important step in understanding also and solving problems also around these concepts. And once you draw the free body diagram correctly, then after that everything is just force balance and moment balance, right? Whether it be statics or dynamics. So if I draw the if I just isolate the first link, then there will be a force at the join 2, at the end where where it joins with link 2, and also at the end where it joins with the fixed base, right? There will be forces at both these ends, and those two forces cancel out each other out, right? Because the link is in static equilibrium. Okay, I hope that's clear. So moving on. So week 5 covers or talks about redundant manipulator and what does redundancy means, right? So redundancy is, so generally in like just as English word, redundancy means that something which is more than what is required, right? So let's say if I am, let me think of a practical example. Basically, in any, designing a system, we like redundancy. And redundancy, why do we like redundancy? Is that because it adds a layer of safety, right? Because let's say it might not be a very good example, but while driving a car, you see that there is a additional wheel there, right? That is kept there. Or in trucks also there is a set of additional wheels, and that is a sort of a redundancy, right? That in case a set of wheels fail or some additional load is put on the truck and we need extra help, so in that case that extra set of wheels or the redundant set of wheels that we have can be used. So anything that is above the bare minimum that is required to do the task is redundancy, right? So in terms of manipulators, if the number of link is greater than the number of degrees of freedom of the task space, then the manipulator is said to be redundant. Okay. So in the, let's say if we are again restricted to the 2R plane, sorry, 2D plane, and if in the 2D plane we are using a three link manipulator, then the manipulator is redundant because in moving to any point in the 2D plane, only two links are required, right? 2 degrees of freedom are required. But if we put three links there, then one link is extra, right? It's not the bare minimum or necessary. So whatever extra links are there, those are redundant links. And you put, you know, two, three, four, how many links you can put. But practically, after a point, it does not make sense to put so many redundant links. But redundancy helps. Now, the additional benefits of having redundancy is that we can achieve certain other objectives also, as we would see in one of the MCQ questions. The fact that we have extra links allows us to do more, right? So let's say we are again in the same 2D plane, and there are also some obstacles in it, right? So let's say you have a tabletop, you have mounted your manipulator on the top of a table, right? And you have put some obstacles on top of it. Let's say some boxes, right? Some two, three boxes you have put. Okay. And now, theoretically, any point in the workspace of the manipulator, you can reach with just two links, right? But it can so happen that some points are not accessible anymore because of the obstacles, right? Then you are in a spot of bother, right? Because theoretically you should reach that point because you have two links, 2 degrees of freedom. But the addition of obstacles have restricted your workspace. Now, in this scenario, in order to circumvent this problem, you would need redundant links, right? Now, if you have three links, it is very much possible that you can reach those points which were not earlier accessible using just two links. They are accessible now using three links because you have more degrees of freedom. You can reach them in more number of configurations, right? So let me just draw it. I'll again try to draw. So it can reach here easily when there are no obstacles. However, when there is an obstacle, it, I mean, it cannot just, let's say there is the obstacle here, right? This point becomes unreachable, right? But if there is, a third link, then and if the link lengths are appropriate, then you can use that third link in order to avoid those obstacles, right? I hope my point is clear. So this is one benefit of having redundant links. There can be other benefits also. Redundant links can allow you to minimize forces or minimize joint torques, right? You can basically achieve more objectives rather than just reaching at a certain point in the workspace, right? So let me put it once again. Having redundant degrees of freedom or having redundant links in your manipulator allows you to achieve more objectives than just reaching your end effector to a certain position. And those objectives could be avoiding an obstacle, minimizing the joint torque, minimizing the forces, right? And those might be beneficial for you in some practical application, right? The second question is the Jacobian of a redundant manipulator is a non-square matrix, right? And let me just so as you would see here, so again this is the 3R manipulator in the unit lane. So if you would do the regular way of finding out Jacobian, that you would differentiate the x coordinate of the end effector with respect to all the joint variables, that is theta 1, theta 2, theta 3, and then y coordinate with theta 2, theta 3. So the matrix that you get is 2 cross 3 matrix, which is a non-square matrix. So as soon as you see a non-square Jacobian matrix, it should be clear to you that that manipulator is a redundant manipulator. Okay. Third question is the end effector velocity x dot is related to the joint velocity theta dot by the Jacobian j, given by x dot is equal to j theta dot. If j is m cross n, then the generalized solution for theta dot to get a desired end effector velocity is obtained using the. Ah, sorry for that, Karthik. So till where did you were you able to listen clearly? Hello, hello. Is it better now, Karthik? Yeah, might be some network issues. I'm actually not in my campus right now, so I'm traveling. So maybe that's why. Yeah. So did you were you able to listen the to the discussion on the redundant manipulators and what benefit does redundancy have? Okay, okay. So after that, I discussed that Jacobian of a redundant manipulator is a non-square matrix because since the each coordinate of the end effector will is differentiated with respect to the joint variables, and since the number of joint variables, that is the number of degrees of freedom, is more than the number of coordinates of the end effector, right? So for a redundant manipulator, so that's why the number of columns will be more than the number of rows. So that's why in case of a redundant manipulator, the Jacobian matrix will be a non-square matrix as shown here. Okay. Hello. Yeah, yeah. I just like I was dropped off from the call for a minute. Okay. So the third question I was going through when you pointed about the audio quality. So this is again the very similar thing which we have seen repeatedly now, that if x if x dot is j theta dot, then basically theta dot is equal to j inverse x dot. Okay. Well, I had to rejoin, right? Is it visible now, Karthik? Okay. Okay. Let's regroup. So we are going to the third question. The third question is very straightforward, that if x dot is equal to j theta dot, then theta dot is equal to j inverse x dot. So the desired end effector velocity is obtained using the pseudo inverse of j, right? So basically x dot is equal to j theta dot, then theta dot is equal to j inverse x dot. And if j is not square, then we cannot take inverse of j. We have to take pseudo inverse of j. And we had seen this in the previous webinar, that how to take the pseudo inverse of j. The fourth question is, given x dot is equal to j theta dot, again the same relation. and J is n cross n. That is not, it's not a square matrix, right? The vectors in theta dot that get transformed into the null space of x dot forms the kernel of the operator. So now again, this is just mathematical terminology, kernel. So kernel means the null space of a operator, and null space of an operator like J here is given by, it's given by identity matrix. Pardon my bad drawing. I minus J. Okay, so kernel of a operator is the null space of a of the Jacobian matrix. So null space of a matrix is the set of, basically the set of vectors to which it is multiplied, then it gives a zero vector, right? So basically AX is equal to null space of, let's say, a matrix A is the solution of AX is equal to zero, right? These are the very, I mean, fundamental concepts of linear algebra. And for a square matrix with which is invertible, right? Which is invertible and square matrix, the null space is trivial. That is, null space only contains the zero vector. So A times x is equal to 0 only happens when x is the zero vector. That is the case when A is a non-singular matrix or invertible matrix, right? But in case of non-square matrices, there is a null space if the row rank or column rank of the matrix is not full, right? So again, it would be better if you would look into few terminologies like rank of a matrix, and whenever the rank of the matrix is not full, we said that the matrix is rank deficient, and that's the case when there is a non-zero null space of the matrix. That is, the null space does not only contain the zero vector, it also has some non-trivial vectors in the null space, and that is what forms the kernel of the operator. So operator here means that the matrix which is being multiplied to a vector, right? As I mentioned, multiplying a vector with a matrix is basically operating the vector through certain operations like rotation, scaling, right? And the kernel of that operator is the null space corresponding to that operator, basically the null space of that matrix. The fifth question is, which is related to, yeah, question. It's mhm. Karthik, it depends on, the dimensions basically. Whether J has, full row rank, full column rank, and that depends whether J is a flat matrix or a tall matrix. So again, if you would have gone to the concept of right pseudo inverse and left pseudo inverse, because it depends whether J has less number of rows, more number of columns, or more number of rows, less number of columns. And depending on that, we define its right pseudo inverse or left pseudo inverse. right? And that only again decides whether it will be J J hash or J hash J. Okay, so both can be possible. Depends on the dimensions of J and its rank. Basically, whether it is full row rank or full column rank. So I would like that's what I can say right now. I like it will be difficult to construct examples right off the bat, but in the next discussion hour, I will make a note that to discuss this both the cases here with some examples. But both can be possible. It depends on the dimensions of J, whether it's tall or flat. Yeah, just check it out on your own also. See few examples to convince yourself. I will discuss this once again in the next discussion hour when I have you know I will to write properly. Today I can't write properly. Okay, so yeah, but both can be possible. Similarly, in the case of pseudo inverse, we can take right pseudo inverse or left pseudo inverse depending on the matrix that we have. So the next question is in n-link serial manipulator, if the joint velocities are contained in a unit sphere, then the end effector velocities are contained, like what is the space of those velocities? Okay, so again, we are trying to relate the joint velocities to the end effector velocities, but here the interpretation is slightly more, in terms of space and physical sense. So the relation remains the same, that x dot is equal to j theta dot, this relation, x dot is equal to j theta dot. And as I have been mentioning repeatedly in this lecture, that the J matrix is doing rotation and scaling of the theta dot space, right? So if theta dot space is a circle, then J space, then operating it with J will transform it into an ellipse in general. It will be transform it into an ellipse. Okay, so in case of n-dimensional space, if the joint velocities are in contained in a unit sphere or a n-dimensional sphere, then the end effector velocities will be in n-dimensional hyperellipsoid. Okay, and that's why I put this image here, that uh, to operating in general operation by a matrix rotates and scales the vectors, and that's what we basically see by doing SVD, that what's the rotation parts and what are the rotation parts and what's the scaling part. So the sphere of joint velocities gets transformed by action of Jacobian into the end effector velocities, and that space is a hyperellipsoid in n dimensions. Okay, any questions? Huh, yeah, 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 go on, go on. Hmm. Yeah, yes, 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 yes. Huh. Yes, uh-huh. Uh-huh. Hmm. Hmm. The locus of the endpoint of that vector is a circle. That's what I guess you are. Yeah, 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 yes, yes. higher dimensions. Yeah, yeah. And same is true for like imagine in the 2D space. So basically, your joint velocity vector, that is the vector containing theta 1 dot and theta 2 dot, that vector will be moving to the end point of that vector will be moving along a circle, right? And if it moves along a circle, then as it and if you see the corresponding end effector velocity vector, then it will move along the ellipse. Okay, so you can imagine that as the joint velocity vector moves along the circle, parallelly you can visualize the end effector velocity vector moving. Its end point will trace a ellipse, right? The locus of the it will trace a ellipse, and similarly in higher dimensions it will be a sphere and an ellipsoid. Yeah, yes. So basically what is happening is that the collection of the collection of all the vectors is being acted upon by that matrix. So that's why we say space, which contains the vectors, right? So it's the entire. So if you take an individual vector, it is transformed and it is scaled and rotated, right? But in order to just collectively specify what's happening to the space, right? Because if we specify what happens to the space, then it's clear that anything that is contained in that space will will be transformed by the same transformed to the same, I would say, like in the same way, in the same manner, right? So that's why transforming a space is a broader way of saying that a vector is being rotated and scaled. Okay. Okay, so the next question is, control of a redundant manipulator can be done by breaking up the task into. So the right answer is a number of tasks with priority. And this is what also I was alluding to when I was saying that when we have multiple, more than the required number of degrees of freedom, then we can achieve more than one task, and we can achieve tasks sequentially such that you know the higher priority tasks are not violated. So again, this is a very in-depth topic of control it's in itself, and I cannot do justice in few sentences. But just to motivate the idea, what happens is that let's say there are three tasks: task one, task two, task three. And by task here, I mean that let's say it would be follow this trajectory. The second task could be uh, avoid this certain area, and third task could be uh, minimize the joint torques. Right? These could be three tasks. And for me, the first priority task is uh, follow the trajectory. The second priority task is avoid certain area, and third priority task is minimize the joint torques. With a redundant manipulator having enough redundancy, I can achieve all three of these, and in such a way that a task with higher priority is not violated when I satisfy a task with lower priority. So that's it's called like hierarchical control of the manipulator. And yeah, I'm not sure if this will come up later in the course, but again, this all these possibilities open up when we have redundancy in the manipulators. So it makes control also quite interesting. The next question is, we have an external global fixed frame A, and a local frame B fixed on a rigid body. If this rigid body only has linear velocity, then what happens? Like, what's the relation between frame B and frame A? So it's pretty clear that if frame B is fixed on the rigid body and the rigid body is only moving with a linear velocity, then the orientation of B is not changing with respect to the fixed frame A, right? Because the rigid body on which frame B is attached, it's not rotating, so the orientation will remain the same with respect to frame A. So very straightforward question. Question 8 is, if a rigid body has an angular velocity, then due to this angular velocity, it also has, of course, again, if there is a velocity omega, then there will be a linear velocity due to it omega cross r. V is equal to omega cross r. So the correct option would be linear velocity. The ninth question is, angular velocity matrix is which type of matrix? So angular velocity matrix, right? So angular velocity matrix is a skew symmetric matrix, and skew symmetric matrices are interesting, right? They are interesting because so what is a skew symmetric matrix? Just to recall, skew symmetric matrix is matrix A is called skew symmetric if A is equal to minus of A transpose, right? So if you do A plus A transpose equal to 0, it means that the diagonal terms must be 0. So for any skew symmetric matrix, the diagonal terms are 0, and also the terms, the off diagonal terms, there is a relation between them too. So they are like e- some sign has to be flipped between the two of set of off diagonal terms. So the bottom line is that any skew symmetric matrix can be uniquely identified using only three parameters in place of the nine parameters that we can possibly have, right? So this condition of skew symmetricity places six constraints on the matrix. I am talking about 3 cross 3 matrices. So a 3 cross 3 matrix in general has 9 elements. Not in general, like it has 9 elements. And if we put six constraints, then there are only three independent variables it can have. So that's the case in the skew symmetric matrix, and it can be just represented by three variables. So what mathematical construct has been created is that a skew symmetric matrix, if we take out the three individual components of the skew symmetric matrix and put it in form of vector, then we call that vector as the axial of that matrix, right? And again, the similarly, a 3 cross 1 vector can also be represented as a 3 cross 3 skew symmetric matrix. So what happens is that the operations like omega cross r, right, which is shown here, operations like omega cross r is equivalent to saying that I am multiplying the skew symmetric matrix of omega with r, right? So a cross product is rewritten mathematically as a matrix multiplication. That's the consequence of constructing this skew symmetric matrix. And for angular velocity, you can write omega cross r as skew symmetric matrix of omega times r. Okay. And finally, the last question is, when a robot manipulator is moving from one point to another, then the angular velocity of the next link is equal to. So again, very straightforward. When the angular velocities can be added incrementally as we move from the previous link to the next link. So the angular velocity, if you would remember in case of a 2R manipulator, so first link has angular velocity theta 1 dot, and second link has angular velocity theta 1 dot plus theta 2 dot. So it's the sum of the angular velocity of the previous link, that is theta 1 dot, and the angular velocity of the own link, that is theta 2 dot. So angular velocity is just added as we move from the inner links to the outer links, right? So okay, so we have finished the 20 questions that we have discussed today, that I plan to discuss today. And yeah, if there are any doubts, then please ask, like, about these topics or any topics till now in general. Okay, if there are no questions, then we can wrap up for today. And I will see you in the next session. Thanks for joining. Oh, bye.